All right, our other main topic for the day is to start section 8.4. Topics in section 8.4 include mass and center of mass mostly for both one-dimensional objects, two-dimensional objects, and even a little bit with three-dimensional objects in certain special cases at least. And we also can take the ideas and generalize these things to non-physics situations. For example, when you're dealing with populations and population densities. Okay, what am I talking about? We need to start simple. Imagine you've got a thin rod, effectively a one-dimensional object. There it is. Of length, I'm going to call the length capital L. The book, in some of their examples, uses like a cursive kind of italics L, and it's a little confusing. It looks like it's a 1. So just watch out for that. A lowercase italics L. It'd be simpler if we just use a capital L. So that's my thin rod. I'm imagining this to effectively be a one-dimensional object. Right. One-dimensional object. There are no such things as one-dimensional objects, right? Rods have some width to them. Even if you made them as thin as you could, each atom, each molecule, whatever, still has a volume to it. How could a rod be one-dimensional? In your imagination. You're pretending it's one-dimensional. No? What is it? Somebody asked you what a point is. Could you tell them the answer? And what would you say? You'd say, oh yeah, a point is, it's a dot like that. Wait a minute, is that really a point? No, it's really not, because it's got some atoms in it. Points are smaller than atoms. Okay. So an atom is a point. No, because you can still make something smaller. Is an electron a point? No, especially if you're talking quantum mechanics. But even if you're not talking quantum mechanics, an electron is still not small enough to be a point. It is super small. We treat it like a point sometimes, but it's not literally a point. A point is way smaller than an electron. Do points exist? Only in your imagination, your mathematical imagination. They're called mathematical idealizations. Same with lines. Do lines really exist? Actually, only in your imagination, though we draw them all the time. I'm serious. I'm not just joking with you. I'm being serious. I'm trying to be serious and funny at the same time. Once again, we can set up a coordinate system. In this case, we can take the coordinate system to be just the x-axis, one-dimensional. And it makes sense to start the start of the thin rod at the origin, say, and that makes this spot be L. This is a thin rod. Probably would make more sense to call it a thin wire, but people tend to use the word rod because they want to imagine it to be rigid and not bendable. Well, what might we be interested in? How about the mass of this thin rod? Or maybe, perhaps more importantly, the center of mass. You ever do this trick before? Take a pen or a pencil, put your fingers like this, and move them together. It's really weird, but you can't stop. You can't really affect which finger moves with respect to the pen or pencil as you go. Sometimes one finger moves and sometimes the other one moves. But any way you do it, it's going to come together at the center of mass in the horizontal direction there. If a thin rod were a uniform density, center of mass would be right in the middle, L/2. But if the density is not uniform, then it's not necessarily in the middle. If it's more dense over here than it is over there, center of mass is going to be closer to where it's more dense, closer to 0 than to L. Here's our next mathematical idealization. Give me an arbitrary point X, well, give me an arbitrary point whose X coordinate is X. Does that make sense? Whose X coordinate is X. Probably better to say whose coordinate is X. And I could ask and try to answer the question, what is the density of this thin rod at X? Density, put the word at in quotes, at X. What is that? What's a density at a point? Does such a thing exist? The
limit is the size of the point.
Yeah, it is a limit, technically speaking. You know, in general density, if you got a three-dimensional object of uniform density, density is mass per unit volume, right? Maybe the mass is in kilograms, maybe the volume is in cubic meters. And how would you figure out the density? Well, you'd have to figure out the mass, weigh it. No, it's tricky. Weight is really a force, not a mass. Okay, don't worry about details. Weighing can help you figure out the mass. And then figure out its volume. What's the quickest way to figure out its volume? Put water in a bathtub and drop it in the bathtub, and at least if the sides of your bathtub are vertical, which they're usually not, see how much the water level goes up to figure out the volume of water displaced. Okay, now that's reality. But in math, we're not doing reality here, we're doing imaginary reality. Volume at a point is really, like David said, a certain limit, but you can approximate that limit by taking a small chunk of the object near the point and figuring out its density, which would be approximately constant if it's small enough. And you can think of that, doing that at every point and figuring out the density at every point, and then saying, hey, that's a function of X. Call it delta of X, lowercase delta. Lowercase delta looks like that. You got to have units. You know, if I'm imagining a rod about this big, good units might be grams per centimeter or something. And note this is a linear density. This is grams per unit length, not grams per unit volume, because I'm imagining this to be a one-dimensional object. That's why. The rod is so thin that I can effectively treat it as one-dimensional in the modeling process. If this turned out to equal 5 grams per centimeter, that means a small chunk of the rod near that point would have an approximate constant density of 5 grams per centimeter. And I could find its mass by taking 5 grams per centimeter times the length in centimeters. Maybe its length is a millimeter, 1/10 of a centimeter. 5 times 0.1 would be 0.5 grams. Yeah, let's imagine a small chunk here. So X is the location of that point right there, and delta X is the width of that small chunk. Then I could say the mass of the small chunk, which, being consistent with our usual notation, I could call delta M, is going to be approximately, and this is an approximation, delta of X times delta X. I love saying that. Delta of X times delta X. Delta of X is a function. Delta X is a number. This is in grams per centimeter. This is in centimeters, and so the product is in grams. The centimeters would cancel. The total mass of the thin rod is the sum of the little masses, which is going to be approximately a sum like this, which now if I let delta x go to 0, magically morphs into an integral. No, really it's a definition. As long as the integral makes sense, as long as limits of Riemann sums for any kind of Riemann sum give you the same answer, the mass, call this capital M, is going to be the integral of the density function from 0 to L. I'm just writing a capital M here for the mass. So if you know this density function, you can easily figure out the mass, assuming the integral is not difficult to do. Now, of course, the integral could be difficult to do. So in reality, you might have to go back to a Riemann sum approximation to actually approximate the integral. And actually, in real life, you're more likely to have data about delta of x rather than a formula for delta of x in real life. You're more likely to have numerical tabular data in a table of values. And so in real life, you're more likely to have to do numerical approximation. That's the mass. What about the center of mass? We're running low on time, so I don't have time to do a derivation of where this formula comes from. But it is in the reading, and I've emphasized a number of times this semester, you really should do the reading. You really should. Not just looking for examples that help you with homework, but really do the reading and try to understand what the authors are trying to say. And in this case, some scientific principles come into play. One scientific principle is called the law of the lever. What is the, or lever, whichever way you want to say it. What does the law of the lever or lever say? You got two kids on a teeter-totter or a seesaw if you prefer. One kid's 20 kilograms, the other one's 30 kilograms. Where should you put the fulcrum to make them balance and not move up and down? You should make the product of their masses with the distance to the fulcrum equal. So if it's a long enough seesaw, put the 20 kilogram kid 3 meters away, kind of far. I guess seesaws are this long at least. And put the 30 kilogram kid 2 meters away. 20 times 3 is 60, and 30 times 2 is 60. Those products are the same. It will balance. So if you take that law, which is an experimental law, you can verify it just with experiments. And you also add on the idea of the moment of an object along a line. What is a moment? It's not a moment in time. It's related to moment of inertia. I don't want to fully explain this either, but here's the basic idea. Just as masses resist linear acceleration, so masses at a distance from a fulcrum resist rotational acceleration. Masses resist acceleration due to forces in a linear direction. Masses resist rotational acceleration due to torques, is the word people use with regard to a rotation, in ways that I'm not going to get into. And to tell you the truth, I'm forgetting the details right now. Those two things come together to give you a formula for the center of mass in this situation. Center of mass. Center of mass. Labeled oftentimes X bar. Or sometimes X sub cm for center of mass. And if you've taken statistics, you know X bar is the symbol for the mean. In fact, this is all analogous to stuff we did with probability. Delta of X is analogous to a probability density function, PDF. And when I integrate it to find the mass, well, with probability at least, that's analogous to the mass being 1. Here, the mass is not necessarily 1 unless you choose units in a weird way to make it 1. It's related. And the center of mass is going to be related to the mean, the average. It's a ratio, a fraction, the bottom of which can be taken to be the mass of the thin rod. What's the top? What's the numerator of this fraction? It's another integral. And the integral is the same kind of integral that gave you the mean for a probability density function, a continuous random variable. X times the density function is the function that gets integrated, in this case from 0 to L. And the mass itself is an integral. It's that integral right there. So this is really the ratio of two integrals. So what kind of problems are you going to have here on this assignment? Excuse me. Well, I'll probably give you another area and volume problem or two. Since we were doing that today. Certainly, you could have problems where you're finding the mass and center of mass of a thin rod. There's the mass. There's the center of mass. Pretty easy. Just do those integrals and calculate this fraction. I haven't explained why this works. Again, the book does that with the law of the lever and moments. I would call it moments instead of moment. You also could have a problem or two where delta of X is maybe not a mass density of a thin rod, but maybe a population density of what? Population density could be people standing in a big long line. Sometimes they're standing closer together and sometimes they're standing further apart. The people are analogous to molecules in the thin rod. Could be even a density of cars on a road. If you got a formula for such a density, it's just an approximation. It's not going to be perfect. And instead of the integral giving you the mass, it would give you the total population. How many people? How many cars? Could even possibly, I'm not ruling it out, give you a problem, and the book does an example like this, where maybe it's a two-dimensional situation. Instead of finding the area of a circle like this, maybe you've got a circular shaped city. And the population density in people per square mile or square kilometer varies radially. Effectively, it's constant along thin rings centered at the center of the city. And you need to do some reasoning kind of analogous to what we did here to figure out the total population. Not ruling that out at the moment. I need to think about it. If I did give you such a problem, and I think there's an example in the book like this, I think you do need to think about these rings, and you need to think about their circumference and their area, as well as thinking about the density function. In the final couple minutes today, let me just mention there's more in the reading that we're not getting into. And I'm not going to assign any problems on this until Friday, but you should read it and try to understand it. There's problems about, and there's reading about mass and center of mass for higher dimensional objects. Let's start two-dimensional. You'll see an example in the book for finding the center of mass of an isosceles triangle that looks like this. By symmetry, it's gonna have constant density, by the way. Constant density. Call it delta. That's not a function of x anymore, it's a constant. By symmetry, in the y direction, the center of mass is going to be along the x-axis where y is 0. I can draw this perfectly symmetric. But what's the center of mass in the x direction? That's the hard part. And so what you're going to read about and have homework ultimately due on Friday about is thinking about slicing this with thin slices to help you ultimately figure out the center of mass in the x direction. And the formula is not going to be the exact same thing as this in these higher dimensional situations. Okay, so that's something to look out for. All right, I'll get your exams and your POs as soon as I can.